Well, in the collision model, we saw that for a chemical reaction to happen, there should be collision of particles. And now collision is what provides what is called the frequency, the collision frequency. Okay. So the collision frequency, the symbol is Z. Now, when particles are colliding, not all collision are going to result in a chemical reaction happening. Only those collisions with the right orientation. For example, if you have got a chemical reaction between nitrogen monoxide and this element. So this element is negatively charged. Now if we consider nitrogen monoxide, oxygen is partially negative. Why? Because it is more electronegative. And then nitrogen is partially positive because it is less electronegative. And so this kind of orientation, a reaction won't be able to happen because a negative and a negative will repel each other. So no reaction. So that means for this reaction to happen, the orientation should be oxygen, the nitrogen, which is partially positive, partially negative, and then reacting now with the element which is negatively charged, and this is going to happen because the negative and the positive are going to attract each other. So you don't just need collisions. Even the collisions which are happening should have proper molecular orientation for a chemical reaction to happen. So that is the second thing needed. Okay. Now, proper orientation is represented by what is called the steric factor, the symbol P. Now, we define steric factor as the number of collisions having the proper molecular orientation. We define collision frequency as the number of collisions happening in a chemical reaction per second. Just how many collisions are happening, that is called collision frequency. But those which are happening with the right orientation, how many are they? That is called steric factor. Steric factor can also be said as a probability that colliding particles are going to collide with the proper molecular orientation. Because it is a probability, steric factor is always less than 1. It's between 0 and 1. As we know, probability can't be above 1 because it can't be above 100%. Now, well, even if we are saying this, for a chemical reaction to happen, we need to supply it with energy because, for example, just this one we are talking about here, for this reaction to happen, because what we want to see is this bond should be broken such that when it is broken, the right element is going to react with the right element there. So for that to happen is this bond which is here between oxygen and nitrogen has to be broken, and so you need energy. Okay, you need energy to break that bond. Not only that, there is also what is called activation energy barrier. For a chemical reaction to happen like this, there is this energy that has to be overcome. So at this point you have got reactants. At this point you have got products. But before you reach to the product, you have got the activated complex on top. So the activated complex is where now you have got a combination of reactants almost going into products. The reactants have already been broken. Now they are almost about to react to go into product. So it is think of it like this, very difficult to climb a hill, but immediately you climb a hill, you reach to the top, you just slide to come down. So that is how simple it is to go from this point to the down. And so what you need for you to reach that point, you need activation energy. So you have got activation energy here. Of course, this point here is the enthalpy, delta H. Now, for you just to reach to the maximum point there, you need to overcome what is called the activation energy barrier. So this here we can see is called the activation energy barrier. That is what you need to overcome by supplying energy which is either greater than or equal to the activation energy. And so for this chemical reaction, because the energy that we started with, we can see if it was 20 here and then 20 kilojoules and then here it is 40, because we started with lower, now it is higher. Then what we are doing is we are releasing energy because the energy of the products is higher. So this is an exothermic reaction. And then if it was like this, the energy of the products is lower, let's say maybe it's 10 and then that's 20. So that means the products took in energy, and so this is an endothermic reaction. Alright, so this is what happens. So we need three things. We need the the collision frequency, the steric factor, and also activation energy, or written as like that, activation energy. Now a combination of the collision frequency and the steric factor gives us what is called okay, let me first remove this. Alright, so we are saying when we combine the collision frequency, that is how many collisions happening in a chemical reaction per second, we combine with how many collisions are happening in the right molecular orientation, that is going to give us what is called the frequency factor. And the symbol for frequency factor is A. So the frequency factor is how many collisions are happening in a chemical reaction per second with a correct molecular orientation. So it's just a combination of these two. And so because of that, the frequency factor is given by ZP. That is the collision frequency times the steric factor. Now using this, we can determine now the Arrhenius equation from this. Now the Arrhenius equation relates the rate constant to the steric factor, the collision frequency, and activation energy. And so the rate constant K is equal to, that is the frequency factor, and then we have got E, that is Euler's number, which is about 2.7. So this is a constant, raised to the power negative activation energy divided by RT. Okay, so where we know A is the frequency factor, the number of collisions happening in a chemical reaction per second with the right orientation, and then we have got the activation energy there. We have got R being the universal gas constant, and then T being the temperature in Kelvin. Well, to bring down the power, we can see there, we are going to introduce natural log on both sides of the equation. Natural log here and also natural log here. Now when we have got natural log of A, B, this means natural log of A plus natural log of B. So when these two are multiplying, and so we have got a multiplication of A and e to the power negative EA over RT. So we can split those. So what we are going to have is natural log of K being equal to natural log of A plus natural log of E, the power negative EA divided by RT. Now, according to logarithms, one of the rules of logarithms is if you've got natural log of A to the power X, we can also write it as X natural log of A. So we can actually bring the power down. So this becomes natural log of K is equal to natural log of A, and then if this comes down, that would be a minus activation energy divided by RT, and then natural log of E. Now natural log of E is equal to A1. So this portion is simply a 1. And so that gives us natural log is of k being equal to natural log of A minus, so what I can do is I can write the activation energy and the universal so I want to write the constants alone, so I'll split it like this. Okay, of course I'm writing the activation energy with a constant, not constants alone, because temperature is not a constant. I just want to have temperature alone, so that will be activation energy divided by R and then times 1 over temperature, which is just the same as here. Of course natural log of E is a 1. So I can start first by writing this. So that will give us natural log of K being equal to negative activation energy divided by R multiplied by 1 over T. And then we have got plus natural log of A. So this is one form that we can use of the Arrhenius equation in a linear form. So it is just from the Arrhenius equation here that we've gotten that one. Now what does this mean if we have got all this? So this is in the form y is equal to mx plus c, where in this case our y is natural log of k, and then our m, that is the gradient. The gradient is negative the activation energy divided by R, and then we have got 1 over t as x. So 1 over t is representing the x-axis, and then our c is natural log of A. Okay, so we can actually see how a graph of this can look like. So where this is the x-axis and this is the y-axis, now we can see that the gradient is negative. Whenever I've got negative gradient, a graph moves like that. Positive gradient, a graph looks like that. So because the gradient is negative, it's going to go in this way. Okay, again, the y-axis is being represented by natural log of k. And then the x-axis we have got 1 over time to have a straight line. On the y-axis we have got natural log of k, and so this line now looks like this. Okay, where the gradient here, the gradient is representing negative activation energy divided by the universal gas constant, and then the y-intercept here is actually natural log of A, natural log of the frequency factor. So basically this is about this Arrhenius equation. Well, we can actually go on and alter it if we are working at different temperatures, and that can help us to make calculations when we are working at different temperatures. So it's also nice to be able to keep this. Perhaps they've given us a diagram. We want to calculate a activation energy from a diagram. How can we do that? So let's just look at it. We see how we're able to get that. Well, even without values. Now let's say we've been given a graph where this is 1 over t, then this is natural log of k. Then we have got a graph which runs like that. Let's say the value here is, okay, let's give it 15. Okay, so this is 1 over, now the temperature we are using is in Kelvin, so let me get the temperature in Kelvin. One temperature that we can get in Kelvin is, let's just say 300 Kelvin. So let's say it is a 300 Kelvin here. But this one is also not temperature really, it is the inverse of temperature. So if you are talking about, if you have got a temperature of 300, that is going to be 1 over 300. Okay, if that is the temperature. And 1 divided by 300 is, so let's say the value here is 3.3 times 10 to the power negative 3, 1 over 300. That's the value that we are going to have if the temperature is 300 Kelvin. And then we have got natural log of k, where k is the rate constant. Let's say the rate constant, so we are talking of temperature being equal to 300 Kelvin, and say the rate constant K was equal to, let's give it 2.1. okay, so if the rate constant was 2.1, and then we are talking of a natural log of K, so if we say natural log of 2.1, what are we going to get? Alright, let's just see the value here. Let's just get as 1.5, because this is the y-intercept. We would have to need the collision frequency and the steric factor. Now, how are we able to determine the activation energy from this? Excuse me. So we are able to determine the activation energy from the data that we have here using the formula. And so all we have to do is we need to determine the gradient of this slope. So we need to determine the gradient of the line. But how do we find the gradient? Gradient is given as change in y divided by change in x. So if we consider this point here and also this point here, change in y, the final y value minus the initial y value divided by the final x value minus the initial x value. So let's say this is the final here. This is where you have y2, I mean x2 comma y2, x2 comma y2, and then this is the initial, that is we have got x1 comma y1. So what is the value of y on this one? So we can see that this is on the x-axis. The value for y is a 0, so that will be 0, and then minus, what is the value for y1? So y1 is there, and we know this is the y-axis, so that is the value 1.5, and then divided by x2. We can see x2 here is the 3.3 times 10 to the power negative 3 minus x1, which is here. No, so on the y-axis the value for x is actually 0 there, so that would be minus 0. So all we have is negative 1.5 divided by 3.3 times 10 to the power negative 3. So to be able to determine the gradient here, we're going to just divide negative 1.5 divided by 3.33 times 10 to the power negative 3. So that is given me negative 450. Okay, that is the gradient. Now, to be able to determine the activation energy, we need to get to the formula. We know that gradient gives what? The gradient is here. This is what gives the gradient of this line. And so we are saying negative E A over R should be equal to the gradient. So that is negative activation energy should be equal to R times the gradient. So that is negative activation energy is equal to, now the universal gas constant is 8.3145 joules per mole Kelvin. And then we have got this value which is here, which is, so times negative 450. Okay, times negative 450. So what are we going to have? This is negative. To cancel with this negative, it remains positive. And so the activation energy is going to be equal to, we multiply 8.3145 by 450. And that is going to give us negative 3, I mean positive, because the negative already cancelled out. So that will be 3741.525. So that is going to be the activation energy. Well, this is energy, and the unit is in kilojoules per mole, or joules per mole in this case. We just consider this unit was in joules. Of course, this gradient that we found is going to be in Kelvin. The gradient is going to be in Kelvin. So why is it that it is in Kelvin? We can see we are saying gradient is equal to change in y divided by change in x. And x is in the denominator. We have got 1 over t. So 1 over t comes in the denominator. And then on top we have got natural log of k, which is y. And that is a constant. Okay, natural log of k is a constant. So let's say it's a constant. Let me just represent it by 1. So 1 divided by 1 over t, we are going to have t. That is why this as a unit of temperature. So the Kelvin is going to cancel out with the Kelvin, so the unit now remains joule per mole. So that becomes the activation energy for this problem then. So that is how we are able to apply the Arrhenius equation in this form to be able to determine the activation energy.